All right, so for today's lesson, we're going to look at a second important or special type of sequence, and that is an arithmetic sequence. The spelling, it looks the same as arithmetic, but it's pronounced arithmetic. And an arithmetic, if you remember yesterday, we talked about what a geometric sequence is. Remember, a geometric sequence is when we multiply or divide by the same number each time. In an arithmetic sequence, we add or subtract by the same number each time. So it's the same concept as a geometric sequence, except we're adding or subtracting instead of multiplying and dividing. In a geometric sequence, you might remember that number we multiply or divide by was called the common ratio. In an arithmetic sequence, the number that we add or subtract by is called the common difference. So that number is called the common difference, and we find it by subtracting any term by the previous term. Remember, in a geometric sequence, we found the common ratio by dividing any term by the previous term. In an arithmetic sequence, we find the common difference by subtracting any term minus the previous term. Okay. If the pattern is to subtract the same number, the common difference is negative that number. So, for example, if our pattern is to add 3 every time, our common ratio or common difference is 3. But if our pattern is to subtract 3 every time, then our common difference would be negative 3. Okay? And then lastly, in a geometric sequence, we talked about yesterday that the graph is exponential in nature. It's an exponential curve, whereas a arithmetic sequence is linear. The graph is linear in nature. Linear, again, meaning straight line. Okay. So those are the lesson notes. Let's take a look at this first set of examples. Okay. So for each sequence, terms 0 through 4 are listed. Number 1, for each sequence, determine whether it is geometric, arithmetic, or neither. If it is geometric, find the common ratio. If it is arithmetic, find the common difference. So let's start with sequence A. Sequence A, 30, 40, 50, 60, 70. So it appears that we're adding 10 every time. We're adding. So A is an arithmetic sequence. Okay. If it is arithmetic, find the common difference. So I'm going to abbreviate that CD for common difference. All right. Our pattern, again, is to add a 10 each time. So our common difference is simply 10. Okay. Sequence B, 0, 5, 15, 30, 50. Okay. When I first look at that sequence, I notice that it can't be geometric because we're not multiplying, because 0 to 5, 5 to 15 is multiplying by 3, 15 to 30 is multiplying by 2. So it's definitely not geometric. As far as arithmetic, 0 to 5 would be adding 5, then adding 10, then adding 15. So even though there is a pattern, okay, we add 5, then we add 10, then we add 15, then we add 20, we're not adding the same number every time. So this is an example of a sequence that is neither arithmetic nor geometric. Okay. And sequence C, 1, 2, 4, 8, 16. To me, it looks like we're doubling. 1 times 2 is 2. 2 times 2 is 4. Times 2 is 8. So this is a geometric sequence. Okay. If it is geometric, find the common ratio. So our common ratio is simply going to be 2 because we're doubling. We're multiplying by 2 every time. Okay, so that's it for number 1. If the patterns you described continue, in which sequence is term 10 the largest? So we have term 0 through term 4. Which one is term 10 the largest? Now, there's a couple ways you can do this. You could go through using brute force and find each term. So 30, 40, 50, 60, 70, 80, 90, and keep going until you get to term 10. Same with sequence B and sequence C. However, there is something that we didn't think about, okay? We talked about how an arithmetic sequence, if we go back to our lesson notes, in an arithmetic sequence, the graph is linear, okay? Whereas in a geometric sequence, the graph we learned yesterday is exponential. So remember, a arithmetic sequence, to do a quick sketch, will look like that if it's increasing. And a geometric sequence will look like that, and exponential in nature. Now the question is, which graph is going to increase at a faster rate? The linear graph or the exponential graph? Well, hopefully you realize that an exponential graph is going to increase, even though exponential and linear graphs are both increasing like I have here, the exponential is increasing at a faster rate. So therefore, because a geometric sequence is exponential in nature, because the graph is exponential, it will increase at a faster rate, and therefore the geometric sequence will have the largest term 10. So in which sequence is term 10 the largest? It's going to be sequence C, because it is the geometric one. Again, exponential graphs will increase at a faster rate than linear graphs. Okay. Number 3, what can you say about the differences between consecutive terms in sequence A? So in sequence A, we already decided was an arithmetic sequence. And the differences between consecutive terms, well, we found that the common difference is 10. So the differences between consecutive terms is going to be 10. It's always going to be 10 by the nature of the pattern. Whereas in number 4, what can you say about the differences between consecutive terms in sequence B? Okay, sequence B, remember we said was neither, because we were increasing by 5, then by 10, then by 15. So the difference is increasing by 5 each time. So increasing by 5, then by 10, then by 15, then by 20, then by 25. So what can you say about the differences between consecutive terms in sequence B? The difference is increasing by 5 each time. Okay. And then let's finish up and look at the second set of examples here. Okay. Jada and Mai are trying to decide what type of sequence this could be. Jada says, I think this sequence is geometric because the value in the value column, each row is 3 times the previous row. Mai says, I don't think it is geometric. I graphed it and it doesn't look geometric. Do you agree with Jada or Mai? Explain or show your reasoning. Okay. So if I look at what Jada said, if I look here, clearly it looks like I'm multiplying by 3, 2, 6, and 18. There is a problem, though. She didn't look at this row. Okay. Term 1 is 2, term 2 is 6, but then she jumps to term 5. Okay. So I'm going to recreate this table down here. Pardon my horrible handwriting. Okay. So term 1, term 2. Now I'm going to add in terms 3 and 4. Okay, so we get a sense of what the sequence really is. So we know that term 1 is 2, term 2 is 6, and we know that term 5 is 18. But they skip 2 terms. So notice we add 4 here. Okay, if I continue that pattern of adding 4, so that would be 10, that would be 14. Notice we end up at the right one for term 5. So even though at a first glance this looks like it's arithmetic, it's actually geometric. I misspoke. Even though that value column makes it look like it's geometric, that we're multiplying by 3, it's actually arithmetic. Okay, so to answer the question, do you agree with Jada or my? We agree with my. Okay, we agree with my because the values are increasing by 4. It's an arithmetic sequence, and our common difference is 4. We're adding 4 each time. Okay, and if we were to look at the graph of it, okay, let me pull up Desmos here. Okay, and pull up a Desmos graph. If we were to graph those points, all right, so our points are 1, 2, then we have 2, 6, so term 2 was 6, and we have term 3 was 10, all right, then we have term 4 was 14, and term 5 was 18, and let's zoom out so we get a better view of this graph. If you look at this graph here, notice it can't be a geometric sequence because the graph is not exponential. The graph is clearly linear in nature. Okay, the graph is clearly linear in nature. If I were to connect these dots and draw a graph, it clearly would be a straight line. And we know that if the graph is linear, it's got to be arithmetic. So to sum up, we agree with my because it is an arithmetic sequence. We know it's an arithmetic sequence because we're adding 4 each time and because the graph is linear.